Basically, the idea is new features. What are the new things that got added to OWL2? And these new features that were added were based on applications. Once they started creating real life applications, and they saw how users are experiencing those applications and what kind of issues were faced. So based on that, a few new features were added. Nothing too big there, but just convenience. It is all mainly convenience. At the end of the day, it's about making it convenient for developers who are, creating these ontologies and writing these rules. A lot of times they are not even, programmers or experts in programming. They're most of the time domain experts. So it should be something that they can quickly learn and do. So expressivity, providing that expressivity was the main goal. So the new features that were provided were broadly, they fall into 6 categories. That's what you see here on this slide. The first one is syntactic sugar, which is nothing but just making the syntax easier and more understandable. So things that were possible before, but just making it easier to express, and maybe with less writing to do. That's the idea. The second aspect is some new constructs, a few new constructs that will provide additional expressivity. And then extending support for data types. We saw that with OWL, there's not a whole lot of data type extensions that you could do. We were mainly dependent on XML, still dependent on XML schema for that part. So, some additional extended support for data type, something like XML schema, things that you could do in XML schema. Then some simple meta modeling, capabilities and additional annotation capabilities. Again, this is all just utility. And then there were a few other minor features. So I'm going to quickly go over each of these categories and kind of show you what was added with a few examples. And some of this maybe you're already seeing or you already saw when you were creating your ontology. So if you see with Protege, you can save your OWL file in different formats, right? And then it supports OWL2. So maybe in the different options it was showing, it was already showing you some of these OWL2 features. And then if you, I know I asked you to save your OWL files as in RDF XML format, but then if you anytime by mistake stored it in OWL format, and if you went and looked behind the scenes how the generated code looked, you might see something similar to what you're seeing over here. Now this first one is about disjoint union. So you can say 2 classes are disjoint in OWL. We saw that already. But then it's a little cumbersome if you have multiple classes, and if you want to say they're all pairwise disjoint, and if you want to say that there is a superclass that provides complete coverage with all of the disjoint subclasses. That is not, it's possible, but it's a little cumbersome in OWL1. You'll have to individually say each of the subclasses are disjoint and then create a separate parent class and say that all of these individual ones belong to it. It's just a little cumbersome. So this disjoint union feature was added. It's not doing anything different. Behind the scenes, it is generating all of those cumbersome statements or triples that are needed. But for the end user, it becomes more easy to express this. So the example that you see over here, so say for example, and again, a lot of these examples you'll see they're coming from the medical world or the bioinformatics world, because that's where these ontology languages have been heavily tested. And they were looking at what is needed more for expressing. So this example here, it's saying disjoint union. So the first one you see is the parent class, brain hemisphere. So it's saying that brain hemisphere is kind of the parent class, and all of the instances in brain hemisphere will either belong to left hemisphere or right hemisphere, not both. So left and right are disjoint. And then complete coverage is through that union class brain hemisphere. Now you can have multiple in here. You don't have to have only 3. You can have any number of subclasses in that list. So there's a second example where you have car door, that's your superclass. And then it is made up of subclasses. Well, subclasses, front door, rear door, trunk door, all kinds of doors. They're exclusive, they're disjoint, but all of them together will form your car door class. That's the idea. Okay, fair enough. That's straightforward, right? And then so that was disjoint union, and then disjoint classes. Same thing here. Previously, you have to list each of the pairs as being disjoint. Here, you can just provide them as a list and say they're all pairwise disjoint. That's what it's providing. So you say disjoint classes and then list all of them. Now here, this notation is using colon. The colon over here, it's for brevity of writing. We're leaving out the namespaces over there. Typically, you would have the namespace, where it belongs, or you'll have the full URI. That's the idea. So yeah, this entire list, all of them are pairwise disjoint. That's what we mean here. In here, we're saying left lung and right lung are disjoint. In here, we're saying the upper lobe, middle lobe, lower lobe of the lungs are disjoint. So disjoint union and then disjoint classes. Those are the two we saw. Then this next one here is a negative object property assertion, a negative data type property assertion. What that means is just kind of the opposite of saying data type property assertion, or so maybe let me talk about this with an example. So say you want to say that a particular instance, so lives in is the property that we're interested in. Typically, we would say person lives in this location. That's an assertion of a property. If you want to do the opposite, you want to say a person does not live in this location. You want to say the opposite of, it's a negative assertion basically. So that's what this negative object property assertion is providing you. We want to say that this patient does not live in this region of France. So that was an object assertion. Similarly, data type data property would be, this person is not of age 5 years old. It's kind of the opposite of a regular assertion. Okay, then it's a negation. And then, so that is the first category, syntactic sugar. Those things were possible, but it was possible through multiple statements, and it was a little more cumbersome. Now here we're talking about new constructs. Now some of these new constructs are related to, this is self-restriction. So it's kind of like a local reflexivity, where you want to say that if there is a process that regulates itself, or some kind of an an object that relates to itself, or restricts itself. So that's what this self-restriction is allowing you to do. So the way it's done is you're creating subclasses. So you're creating a subclass called auto-regulating process, and it has a self-restriction. So object has self is the new construct that got added to indicate this self-restriction. And you're saying that, and there are what kind of restriction it is. So that's basically a property. In this case, in example 1, it's the regulate property that applies to itself. In the second example, this is from whatever chemistry, it's phosphorylate that applies to itself. So some kind of a restriction that applies to itself. Again, it's very specific to certain domains where these kinds of constructs were useful in providing descriptions. So that's why they got added. Then things related to cardinality. Cardinality of properties. There were already a few things that we could do. In OWL, here a few more got added. So object min and max cardinality and exact cardinality. Previously, all we had was cardinality. That's it. Here now we min, max, and exact. So they've separated it out. And the other thing so let's see how that's getting used. So you can say object min cardinality. And this syntax that you're seeing over here, I mentioned earlier, if you saw how your OWL file would look like, if you chose the OWL syntax, you'll see this kind of a syntax being used. you can try that out with Protege. It will generate statements that look like this. So min cardinality, we're saying that the property has direct part. Here it's not only just saying min, you can further qualify that. It's not only specifying the cardinality value, but you can qualify it with some kind of a property. Yeah, so things like, I missed out on this example, I should have. So with OWL, you can mention cardinality. You can say that person has children and the cardinality is 3 or something like that. You can say that in OWL1. But the thing that you cannot say is, so you want to further qualify that cardinality and say that you're trying to create a class of persons that have at least 3 children who are girls. So there's a further qualification, at least 3 who are girls. So that kind of a thing you cannot do with OWL1. And that's what was added here. And with these examples, that's what you see. So we're saying that has direct part, there's at least 5 parts. There's a minimum of 5 parts that are of type thing. Here there's a minimum of 1 part, sorry, it's an exact. There's exactly 1 part of type frontal lobe. So there's that additional qualification that you're able to add to cardinality. I think that's the main takeaway over here. With cardinalities, you can also additionally qualify them with a property value. So there's min, max, and exact. Then you can have, you can construct reflexive object properties. So when you say same blood group, so previously we could say property is symmetric. You could say it's transitive. Now there's additionally, you can say that is it reflexive or not. So when you say an object property is reflexive, what that means is everything that has the same blood group is it's the same as itself. So, or if you say part of is reflexive, then you say everything that's part of is itself. So it's reflexive. It's no, because you're saying reflexive, now you can also say irreflexive, the opposite of reflexive. So proper part of is an example there. It's not irreflexive. I mean, it is irreflexive. It's not reflexive, it's irreflexive. Same thing with bound by and flows into. Nothing can flow into itself. Things cannot be bound by itself. So these are irreflexive properties. So we can indicate those. And then you can indicate asymmetric as well. Previously we had symmetric, we said X is symmetric to Y. Now you can say something is asymmetric. So, and then there's okay, we had disjoint classes, but we didn't have disjoint properties. So disjoint properties got added, disjoint data properties and disjoint object properties. So you say here, so what that means is if you have 2 individuals that are connected by a certain property, and if it's disjoint with something else, then those 2 individuals cannot be connected, cannot be related by that other disjoint property as well. It has to be one or the other. So connected to and continuous with or disjoint. Kind of makes sense, right? When you say 2 instances are connected to, they cannot be continuous with as well. So that's the reason they're disjoint. Similarly, the other example you see here is start time and end time. They cannot, no, with object properties, the connected to and continuous with makes sense. The second example is related to data properties. When you say data properties are disjoint, then those values, they must be different. So say you have a surgery and the surgery has a start time and an end time. So those 2 properties, data properties are disjoint. So the start time and end time cannot be the same for a surgery.
That same object, object by thing. I mean, no start time can be, or rather than inside of that object, the start time cannot be.
Yeah, it's for a particular instance that we're talking about. If the instance is the same and they have, say you have surgery XYZ, one particular surgery, it has a certain start time and certain end time. So we're saying because start time and end time are disjoint data properties, the domain that it's applying to, that the property is applying to the range value cannot be the same for both of them. That's what it means. Yeah, it is for specific instances. And then there is this object property chains. What this means is kind of composition of properties. OWL1 could not handle composition of properties. Whereas, with in OWL2, this object property chain was added to be able to do that. This is again going back to the same kind of idea where when you write rules, say you have the ancestor rule or the descendant rule, you kind of compose it with another one. So it's the same idea. So here we're using located in and part of. So saying if X is located in Y and Y is part of Z, then X is located in Z. So it's a composition. So you can specify those kinds of properties as well with this object property chain construct. So these were, and I believe this is the last new construct that was added. It's key. So you notice that there's no concept of a primary key, right? In with OWL, but they added a property to kind of keep track of that. You can say any one property is the key, and so which means that value is going to be unique, across all instances. So an example here is a registered patient has a waiting list number, and that waiting list number is unique to the registered patient. And we say that the waiting list number is a key. So you can, so has key can be used for that. And similarly, if you have like say social security number or something like that, those can be indicated as keys. So the way that will work is, so these rules over here, again, this is OWL2 syntax. Assertions, so you'll see these statements as assertions, which is, you create your schema and then you create your instances. So the assertions, you're asserting in this case that this patient, an individual or an instance, is of type registered patient class. So that's the class assertion. You're indicating that an instance is of this type of a class. Then data property assertion is where you're actually giving values to the data properties. So we're saying that for this instance, this patient, we're basically defining the data property has waiting list number. So this is the property name, this is your domain, and this is your range, the value of it, that's your range. Okay. So in OWL2, you see this kind of notation. And again, if you think about it, the idea is, as we advance and as we're creating more applications, we want to, the syntax should be such that it's easily, we want it to be readable, something that makes sense to humans. But at the same time, we want it to be lightweight, so applications can quickly process it and use it. You saw that with the XML syntax, it gets really, a lot of, the file size itself gets larger. So we're trying to minimize that. So the idea is, so you have class assertion to indicate the instance, you have data property assertion to indicate the data property, and then you can, in your schema, you have a key defined. So that has waiting list number is the key. So that has to be unique across all instances. So it'll make sure when you add that data, it'll make sure that this number is not already used up by some other instance in your database. Okay. All right. So those were some of the new constructs. Data types, as I mentioned, there's not a whole lot related to data types within OWL. So that was a limitation. So a few things like, the ability to not just use integers, but the ability to say that adult age is age 18 or greater. So basically include 18 and anything, above 18. So, so we're adding a data type restriction here and saying we're specifically looking for integers where the minimum integer min inclusive is 18. So you start with 18 and above. So, that's a way to define, say, adult age. So with these data type restrictions, you're able to create new data types of this sort. Here, this example is a little more complicated, but the idea is OWL2 is able to do these. I want to say that the admission temperature. You compare. This is the case where, say, a patient is getting admitted into the hospital. You want to check their temperature before they're admitted into the hospital, and there's a certain criteria for admission. So you compare what their temperature is when they're being admitted and what the allowed is, and you compare them. So that's what this data all values from is doing. It's taking the two values and comparing them. So this data comparison construct is there. It's a function that takes in two arguments, and then you can indicate what kind of comparison do you want to do with those arguments. So here, this first thing over here is passing the arguments, and the second part is doing the comparison on it. So there are different comparison operators that are possible. Again, the nice thing is the editor Protege will help you with it'll assist you with all of these different features when you're creating your ontology. Now, what was your experience like with Protege when you were creating your ontologies? Was it easy to use? Did you feel that you found what you needed without, again, there's a learning curve with any kind of IDE, but the purpose is that to make it easier. Like I said, people who are creating ontologies or involved in ontology engineering may not necessarily be programmers or expert programmers. They have basic knowledge. They have more of domain expertise. So the way you would use these, once you have a restriction, so you can create a data type restriction like this and apply it when you create, you can create a new data type definition called adult age and apply a certain restriction on it. So that's how you're, creating these new data type definitions, and then you can use them in your ontology. That's the idea here. Now there's a number of other combinations that you can use. You can use the data union of, intersection, complement. So, once you bring in those different combinations, it just provides more options. So here we're, you want to create the complement of adult age. So maybe you want to create something like a kid age or a child age, or a non-adult age. It's kind of, you can use the data complement of to create the opposite of adult age. So those were data types and how you could create new data types. This fourth category is just meta modeling capability. So this is what I'm, I was trying to refer to. You've probably seen some of this. It just did some, made the syntax simpler. So probably you saw a lot of declaration statements in the OWL file. So what this means is you're declaring that an instance person is basically a class. So that's what we're declaring. So it's in the form of declarations now. When you go into Protege and you say new class and you create a new class called person, behind the scenes it's generating this statement and adding this to the OWL file. Then say you make a class assertion. So say you create an instance. So you have a class service and you create an instance S1, then that would create a class assertion statement of this kind. This is again just syntax, just so you're aware. If you see an OWL file with declarations and class assertions, you know how to read it and you know what that means. So here all we're saying is S1 is an individual of service. That's what it means. Similarly, when you create an object property and you say S1 is connected to person with the property has input, you would do this in Protege. You would create an object property has input and you'd connect S1 and person. S1 is the domain, person is the range. What that will do is it will create this assertion statement in the file behind the scenes. Okay, so these are little, again, it's different from RDF XML is the point. And these were added in OWL2. All right, a few annotation assertions. It's basically annotations and providing, further descriptive information about an instance. Now, these days, these annotations are getting used a lot when you're trying to, do machine learning or something on existing ontologies and try to compare two ontologies for similarities or something like that. Their identifiers themselves may not mean anything, or, it's hard to understand their meaning. There's more semantics in these comments or labels. So those are getting used a lot. So there's more focus on these annotations. There's additional ways of providing those annotations. That's what this is. So you'll basically see this annotation keyword, and then within parentheses you have the comment, and then a a description. Right, and then declarations. So declarations, we already saw how this the codifying it uses this declarations syntax. Yeah, here's the example. We're declaring a person as a class. We're declaring Peter as a named individual, and then we're declaring that the car 0 colon some identifier is basically an instance. It's declared to be a class. So remember, you look at this. So when you say declaration class, so you're creating a new class. When you use named individual, you're creating a new instance. So you'll see, again, you can, any ontology that you have that you previously created, go back to it and save it as an OWL file and look at the code that's generated. You will see these kinds of statements in there. It's just another way of, it's just syntactic sugar, all of this, another way of representing. Oh, the last and kind of interesting aspect is the top and bottom properties. Remember OWL thing and OWL nothing kind of thing captures all the objects and nothing captures nothing. So similarly for properties, they added top and bottom. So top property, top object property, it says that all pairs of individuals, any individuals in your ontology are connected by top object property. And then the bottom object property, no individuals are connected to each other by bottom object property. That's the idea. Honestly speaking, for me, it's been hard to wrap my head around the utility of this in real life. I mean, I'm sure there is. That's the reason these were added. And sometimes it becomes important to have these for some kind of proofs and, for theoretical purposes behind the scenes. But, how one would, maybe bottom, I can still see that. You're trying to say that all there are no individuals that are connected by by a certain property. If you want to represent something like that, you can use the bottom object property. But the important takeaway over here is, like you have thing and nothing for classes, you have top and bottom properties for properties. So this is for object property, top object and bottom object property. For data properties, also you have the top data property and bottom data. You just switch the data and the object part. All right. So that said, the last thing, URIs. So we used URIs. Now it's called IRIs, which is basically internationalized resource identifiers, to take care of the different, the internationalization, of strings and how they're used. So IRIs are used. OWL2 supports IRIs. That's the idea. That's everything about. Well, that's like a kind of a summary of OWL2 and what got added. I would say, for the final exam, how would you prepare, or what's the takeaway from this? Right, having that understanding of those 6 different categories, and at a high level, what are the different things that got added under each of these levels is what you should know from an exam perspective. If you want to see more examples or details, that link that I provided to OWL2 primer, it has a lot of additional examples for each of those constructs. Okay, so that